So in this installment, we're going to talk about the ballistic pendulum. And you've already watched a video on what a ballistic pendulum is and the basic operation of it. And so I've got a composite image here of a ballistic pendulum in operation. Let me first situate you in terms of where we are and the thinking we're going to employ in looking at a ballistic pendulum. So we are in the field of mechanics. We could look at a ballistic pendulum and talk about the kinematics of it, which we certainly can do. Although it's not going to be helpful for us here, we could certainly deal with the kinematics of it. We are going to deal with the dynamics of it. And if we remember that kinematics is about what is happening, and the dynamics is about why it happens, the rules, laws, and principles that dictate and govern that. And what we've also seen is that there are two fundamental approaches to why, and those are the conservation of momentum and the conservation of energy. And we will use both of those in a ballistic pendulum. Now, we could also speak about forces, but we have yet to study forces in depth yet. But we know what they are. We know they cause accelerations. And those accelerations, of course, are changes in momentum, produces change of momentum and changes in energy. So we are going to apply both the conservation of momentum and conservation of energy to this situation. So let's first apply and use the lens of momentum. Now, what we know is that momentum, linear momentum, is always, always, always conserved. We can count on that. Linear momentum is always conserved, and that's our P0 equals P. The initial momentum equals the final momentum. The total momentum of the system remains constant. So what we have is we have a little projectile that has just been released like this, and it has momentum. And it has momentum. We have the momentum of the projectile, so momentum P. And then afterward, during the interaction, the projectile gets embedded in the catcher or the receptacle, and the two move off together. Now, in the past, we've seen this happening in a line. In this case, it takes a curved path, but the result is still the same. Linear momentum is conserved. And so what's unique about this, then, is it deviates from that horizontal line and climbs upward. But what's interesting, then, is, and what is useful to us, is that the instant before impact and the instant after impact, the linear momentum is conserved, and that's key. It's the immediate instant before and the immediate instant afterward. And the moment that projectile starts to deviate from that horizontal linear path, then the nature of the system changes. And we'll talk about that at the end. But right now we're looking at those two moments in time, the green dots, the instant before and the instant afterward. Well, the instant afterward, we have the new momentum of the initial projectile and its receptacle. The momentum of the projectile plus the receptacle. So beforehand, that's just simply the mass of the projectile times the velocity of the projectile, which we'll call v. And then afterward, we have the mass of the projectile plus receptacle and its velocity we'll call v prime. Now, MPV stays MPV, but on the other side, we have mass of the projectile plus the mass of the receptacle, all times that velocity v prime. So we can find then this, if we measure the velocity beforehand, we know the velocity beforehand, we can measure the mass of the projectile, measure the mass of the, and the mass of the receptacle. So we could then solve for v prime, and v prime then would be MPV over MP plus MR. And so when we look at this overall, we probably recognize this of our two types. We have bouncy and sticky collisions, and this is the case of a sticky collision, which we know is inelastic. It's an inelastic collision. So we know the linear momentum is conserved, and we know the energy is conserved, but being an inelastic collision, the kinetic energy is not conserved. So we are able to, knowing all those things, find out the velocity initially right afterward. Now, the sidebar here about what happens to the momentum afterward, you are probably dying to know. Well, what we know if we look at the very end of this trajectory, way up here, the projectile and the receptacle have a velocity equal to 0. So they have experienced a change in momentum. They did have a forward momentum, but now they have their change in momentum is in this direction that they experienced. So for the total momentum of the system, which no longer it can be the particle and the receptacle, we need to bring in the Earth. This pendulum catcher, the receptacle, is tied to the top, which is tied to the base, which has friction on the ground, on the table, which is connected to the Earth. So what happens is that we then get a change in momentum of the Earth in this direction. If you envision that in your mind's eye, you could imagine that this whole system, the red platform on the table, on the Earth, for that to come to a stop, it will pull the Earth in the other direction. And of course, since we have the mass of the Earth, delta V, and we have the mass of the projectile receptacle, delta V, we can see that since the mass of the Earth is so large, the delta V will approach 0. It'll be infinitesimally small. So that's what's going on with the overall momentum of the system. We can look at the system as when it's kind of free hanging, but once there's a force starting to be exerted on the particle, that force is being provided ultimately by the Earth, and that is the action-reaction pair there. So let's move on to the lens of energy. We said that the total energy of the system is constant. That's the law of conservation of energy, which is always, always true. Well, let's put in our little blue particle. We have our little blue particle before. And if we look at the total energy of the system at this time, that total energy of this system is the kinetic energy. It's the initial kinetic energy. And the instant before, we have that instant in time, we have the time during, we have the time after, and we have a whole host of times afterward. And in fact, when we get to the end up here, we know that the kinetic energy will be 0. And that there will have been a transformation of kinetic energy into potential energy. And so we have a delta Z, in this case, a change in height. So that means a change in potential energy, gravitational potential energy. So the question is, what happens to the energy in between? We know there's this kinetic energy of the particle. We know there's this potential energy at the end. But what's happening otherwise? We know that as this particle, after it's trapped in the receptacle and it moves up, we expect its velocity to go down exactly as much as the potential energy increases. So the question then is, at the instant before, which is right here, and the instant afterward, how do those two kinetic energies or the energies interchange? Well, we know that this is an inelastic collision. We know it's an inelastic, a sticky collision, and so we know the kinetic energy does not remain the same. So afterward, what we initially have at the moment afterward is we have some kinetic energy, but it is not the original kinetic energy. That some of that energy is lost in the sense of thermal energy and vibrational energy and sound energy. But now this term in the middle, the kinetic energy, the new kinetic energy and the energy lost will be equal to the initial kinetic energy. And then at the very, very end, that kinetic energy will be 0, and we will have gravitational potential energy, and that's still that amount of energy that was lost due to thermal energy and sound energy. That sound energy will dissipate as it spreads out. It gets thinner and thinner and thinner, so we can't hear it. But the energy's there nonetheless, and the thermal energy, and so the receptacle and the ball are still warmed up. So at each of these three terms are all equal to each other. But what we want to focus on now is just these two. So I'm going to rewrite those down below. EK prime plus E lost equals EPG plus E lost. Now the E lost are equal. So they're the same on both sides. We could subtract them both, and now we are left with the kinetic energy prime being equal to the gravitational potential energy. So, in other words, this kinetic energy that exists right there is equal to the gravitational potential energy there. There is this exchange. Delving deeper, we have 1/2 mv, and we'll call that v prime squared because there was a velocity before and there is a velocity afterward, which we know is different, and in fact it's less. And afterward we have mg delta z. We may notice then that there is an m on both sides, and we should ask ourselves, are the masses the same? Well, the kinetic energy is of the projectile and the receptacle, and the potential energy is of the projectile and the receptacle. So these m's are equal to each other. So we are left with 1/2 v prime squared equals g delta z. Now, what was not intuitive from the beginning is that this relationship at the end is independent of the mass. It doesn't matter what the mass of this particle is. The result will be the same. It will depend only on the velocity, and that will produce a resulting change in height, all of which is independent of the mass. So if we try to find this velocity afterwards, so we can determine the height, the delta z, from using a couple techniques, which I'll show you. So the question then is, what is this v prime? Well, v prime squared then will be equal to 2g delta z, and then v prime will be equal to the square root of 2g delta z. So we have this change in height here, delta z. We have our masses that we know. We have that initial velocity. All we need is to determine that delta z from a couple different methods to find that velocity. We're going to pause this episode here and add another shorter video where we will go into the change in height.